of us are here. Okay, this is going to be recorded, so I'm going to start now that we have a couple of folks here with us. Hopefully the rest will come and join. You should have access via Dropbox to the slide deck, which unfortunately those who are remote are not going to be able to see well because this whole thing is a real mess in terms of how the presentations work. But okay. So first order of business is to actually deep dive into pyretic. And the purpose of this session right now is going to be to basically give you an understanding not of how pyretic works from the user standpoint, but how pyretic works primarily from a implementer standpoint, someone who's hacking, mucking around with the code. So I've got some slides here. We're going to go through them fast, then we're going to actually dive into the code itself. So just a couple of ideas that are important for implementation and that will connect to hopefully your understanding of the language from a user's perspective. So what we were trying to do with pyretic was provide a modular, sort of higher level interface for being able to program software-defined network hardware. And the interface to this hardware is OpenFlow. So you've got this low-level hardware table that lets you, that gives you bit patterns, actions, priorities, counters that are associated with each line. And what we need to do is we need to extract the structure, all these various features and interdependencies, in such a way that we break them into a set of new components which can be combined modularly. So we're going to do interface redesign here. And the idea that pyretic uses to achieve this, and this is an idea that's important if you're a user of the language and also important in the implementation of language, is that we're going to abstract each piece as either a function that basically is going to take an input packet at a particular location and send it through the flow table and produce a set of output packets. So this flow table, in terms of its actual behavior, its semantics, its meaning, not how it gets it done, but what it does, ultimately in terms of input and output, is described in this functional way. And pyretic basically takes the packet as a slightly abstracted thing from the actual concrete packet. So you've got these fields like switch and location. So it's just a function from located packets to located packets as opposed to a packet and its location separately. So from now on, when we say packet, we mean a pyretic packet that has fields virtually for import, output, and the switch that packet's located at. And basically, in terms of how this works, and this should be familiar to everyone, but we're just going to go through a quick example of abstracting, say, a higher level policy flood as a function. Well, if we have a packet that comes in, switch C at port 1, then the function is going to be evaluated and produce an output set that consists of one packet going out C2. That is then going to be carried across the topology, because that's the nature of what a topology does. And now we have a packet B that's at location 2. And I'm just annotating the locations. These are all actually just carried in the packets with them in the pyretic system. Now we get an output set of 2 packets, one at port B1, the other at port B3. These 2 are carried out. One goes out of the network entirely, maybe to an NTOS, maybe to another network, but it's out of the scope of our SDN network. And the final packet goes to A1. For those who are watching in the audience, we're going through the animation, I think the 3rd slide of the deck, packet functions, precise and abstract. And finally, when we apply this flood function to our packet at A1, we see there are no more packets to be sent. So that's abstractly how we can represent complex behavior using a functional abstraction. How you actually build flood up from a set of as a policy from a user's perspective, we're not going to go into right now, but we might actually go into it because it's already provided in the code. So we'll have a peek at that later. But for right now, high-level bit is we're going to take each piece of this flow table and we're going to abstract it either as a primitive function in and of itself that does something when taking a packet, or as a combinator that takes 2 or more functions on packets and outputs a new function that does some type of combinating behavior. And we'll see the two main combinators momentarily. So these are all the things that we need to abstract with functions. So we're looking at bit patterns, actions, the counters. Things that we're going to use combinators for are the sort of if-then nature of each rule in our open flow table. So match a pattern, then do an action. We're also going to use another type of combinator to represent multiple actions in the same rule, or multiple rules that are all working on potentially different packets. And so in terms of, and we're just going over the high-level structure of language, so now this is a user perspective. We're just going to run through it really quick for everyone to just get one more look at it. So we have a filter match a field equal to a value. If we apply that to a packet, what we get is the output set containing just that packet if the packet's field is equal to a value. Otherwise, we get the empty set. And that's a filter. That's the first of our primitives. The second primitive that we have abstracts the action port. We previously, with match, abstracted the bit pattern. Now we're abstracting the actions. So if we modify field equal to a value, apply that to a packet, then the output set will be that packet, a copy of that packet, identical in every way, except with its field being set to the new value, if it didn't already have that value. And that's the singleton set there. So that's our second primitive function. And in fact, forwarding is just a special case, right? In pyretic, because it's just modifying an output field. So now we've got just a couple more primitives. Actually, I think there's 6. I lied to you. So we want to be able to distinguish from cases where what we might mean in our flow table is, or where we have a flow table, we want to compose it with another flow table in sequence. So we say, want the first flow table to change some packet headers for some subset of the packets. And for other packets, then we're going to not change anything. Now, that's not something you can explicitly say in OpenFlow today. And for those of you who are in the audience, we're on slide number 11 of the slide deck at this point. So what we really want is we need something to say, hey, just leave the packet alone, pass it through unchanged. Contrastingly, we might have a rule that tells us we want to firewall packets and drop them. That looks exactly the same in OpenFlow. You can't encode this stuff explicitly in OpenFlow, but in pyretic, we're going to give you abstractions to encode that stuff. So identity of a packet is just always equal to the singleton set containing that packet. Likewise, drop of a packet is always the empty set. So here we can specify those. Those are 2 more of our primitive functions. They come in a pair. And finally, one last pair, and this is to abstract the idea of having counters associated with each flow table entry. And so, if you want to send a packet to the controller, and for those who are following along on the slides remotely, we're now at slide number 12. So we might want to say, hey, forward our packet to the controller for further handling. Or contrastingly, we might want to say, hey, we're just putting this rule here. We don't want to do anything with that. And it's not even really so much that we want to pass it on to something next, but we want to count it. And we want to make a space to count it, and we're agnostic to what happens next to it. So again, we want to have a special way of saying that, and so we have 2 additional things, and these are going to be important when we come to the implementation momentarily, namely the idea of a forward bucket applied to a packet, and what this is going to do to that packet. In the data plane is output nothing, so nothing is going to go forward, but the packets themselves are going to be sent from the data plane into the control plane, particularly to a corresponding data structure maintained by the controller. So every time you create a new forward bucket, the runtime system will create a new data structure and will make sure that any packet that is sent by the policy semantically to that data structure actually gets onto the controller into that particular data structure. Okay, that's forward buckets. And if we want to say count, well, that's a count bucket. Same semantics, but the data structure's changed. Namely, it's a data structure that counts things as opposed to a data structure that gets every single packet. So it's going to count the number of bytes total and the number of packets total. Any questions about any of that? And if anyone in the audience wants to ask a question, just please unmute yourself. I've got my volume up. Yes, is there a question? I'm just going to quickly switch to the view here. I don't see, I don't hear anyone saying anything, so I'm going to assume that there aren't any questions. Okay, and I don't see any chats or any other little boxes popping in. Okay, great. So, yeah, so you do have a question. Good.
Hexadecimal number in the previous slide.
So we're flipping back. So this is the special code that's used in OpenFlow so this is what OpenFlow calls a virtual port. And it's their virtual port, meaning send to controller. There's another hex code that corresponds to, there are a bunch of different hex codes that they have that correspond to various things. I think one's to sending it out all the ports. Yeah, so there's a flood one. There's also an all one, which is different than the flood one, because the flood one uses a minimum spanning tree, whereas the all one doesn't use any topological information. And they've got a couple of others like that. Yeah, there's one to send straight back out the import. That is correct. So by default, when you say OpenFlow forward out port 1, that means forward out port 1 unless the packet came in port 1. Whereas with Pyretic, if you say forward out port 1, that's exactly what you mean. So it doesn't matter where the packet came from. It could have come from port 2, 3, 15. It could have come from port 1. It'll still get forwarded right back out port 1. Question?
Yeah, I think you said this, but just make sure. So if you count the packet, it's always going to go to the controller.
What?
If you do the count bucket, that packet is always going to go to the controller, so that it counts correctly.
So if you do a count bucket, the packet may not go to the controller. And we're going to see that in the runtime within the next couple of minutes. Okay.
Does the OpenFlow switch has rules that they count patterns?
Yeah.
All right. So let's move on. And these are all the primitives. The compositors you should all be familiar with. So I'm going to move over this really quick. Parallel composition, which is taking two functions and outputting the set union of their two outputs. And sequential composition, which is going to take those same two functions and instead more or less output the second function applied to the first function applied to the packet. And this is the actual formal definition. But we'll also go through this in the code, so you'll have a better idea. It'll help with your tuition. So these are our combinators, parallel and sequential composition on multiple, and we also have negation of those filter primitives that we showed you beforehand. Or things built out of filter primitives. So with this, we've got a complete interface redesign. So we've gone from the world of OpenFlow to Pyretic's domain-specific language. And this is a language it shares with other members of the frenetic family of languages. Some depending, we'll call this NetCore, but there are a whole bunch of different variants. In any case, this is it. And now that I've shown you all that, I'm going to slow down, and we're going to actually dive into the runtime system. Any questions before we do that?
Can I make one quick suggestion?
Sure.
That we go around the room and do introductions just to make sure everyone knows each other?
Okay, we can. I was thinking we would do that after the first session, but
No, never mind.
did that? Okay.
It's up to you.
Well, actually, I mean, this is a nice quick stop point for people to take their breath, and you know.
My 2 cents is probably not to try to have people on the bridge do it because it's kind of complicated.
But I'll move this microphone towards the moment. So folks on the bridge, we're not going to have you introduce yourselves right now. But what we will do is have the folks who are here physically introduce themselves, and I'm going to turn. I'm going to. Yeah.
My 2 cents is trying to.
Can't see us anyway.
Trying to optimize for the bridges.
Yeah. I hear. Okay.
My 2 cents is to try to.
Fair enough. Okay, so you know, you guys may be able to hear on the bridge, maybe not, but yeah, everyone here, go around.
Want to start?
Sure, I'm Nick Kingster from Georgia Tech.
I'm Grace from George Washington University.
I'm Sean, and I'm Dr. Gupta from Georgia Tech.
Naga, I'm a third-year PhD student.
I'm Mark, I'm at Princeton.
I'm Aditya, I'm an intern from summer at Princeton.
Hi, my name is June Kim. I'm a PhD student from Georgia Tech.
Hi, my name is Mohammed Shabal. I'm a PhD student from Georgia Tech.
I'm Jen Rexford at Princeton.
Okay, so we got everyone's name. Should we do one more round where you actually say why you're interested in being here? Or not? Yeah? Okay. Take it back.
I think we have a lot of different projects that are building on pyretic, both as applications and also perhaps adding various other
I'm interested in SPN and I'm working on a video platform. I think maybe Pyretic will help me on my project.
And feel free to say your name a second time. That's always helpful.
I'm Sean, I'm working on an essay project, and it's built on top of pyretic, so the background's kind of
Hey, I'm Rupit, and I'm working on SCX project, which is also built on top of pyretic, and also on kinetic, which is also built on top of pyretic. So I work majorly for SCX on optimizing the compiler because we had scalability issues with combining compilation of that. So I want to talk something about that also. At the moment, I'm not working on a specific project that is a pyretic, but I've been part of the support team.
I'm Marky, and I'm working on a visualization tool to visualize the network pyretic to help with developing.
I'm Aditya. I actually graduated from Princeton in 2010 as an undergrad, and I took Jen's 08 computer networks course when software-defined network, as you said, wasn't really even a thing. And so when I heard about it, it seemed really fascinating. And I'm sort of interning in the summer, hopefully playing around with Pathway to use what Mark's building around visualization to show how certain types of packets are traversing the network.
Hey, my name is June. I work on a project called Kinetic, which is built on top of pyretic. And Kinetic, you actually build a network policy using bias state machine, and also provides formal verification coverage functionalities to it. So as Josh is leaving, I thought I should pick the brains of Josh before he leaves, so that I can continue working on the project.
Wow, that's pick my brains.
Yeah. So yeah, this is Shabal. So actually, I'm working on mostly on programmable data planes, and one of the things that I'm working on right now is to come up with low-level language abstractions other than OpenFlow. And then I like the idea of how pyretic actually compiles to OpenFlow, but I'm looking into details like how to compile pyretic onto these different programmable data planes, the new language we are working on.
All right, and I'm Jen, and we have a bunch of different projects going on that are either using or extending pyretic, so I wanted to get more familiar with guts.
Awesome. Okay, so we've now done that. Sorry, folks on the bridge, you're not going to get to introduce yourselves now, but maybe during the break we'll try that. I don't know. So now I'm going to go back to the slides, and we are actually going to skip over a couple of the slides because I think that I'd like to. Okay, there. Yeah, we're going to go to slide 21. Here we go. Yeah, we'll go to slide 21 and just start from there. Okay, so behind me, we are seeing, and for those of you who are looking at slide 21 separately, what you're seeing on this slide is a whole bunch of OpenFlow gunk. And what this is actually, and just flip back one page to page 20, these three simple pyretic functions or modules. So balance, route, and monitor. Each can be written in pyretic in a very simple way. They're on your slides earlier. You can look through the details on your own time. But suffice to say, they're nice, compact pyretic statements. And if you want to combine them together such that first we load balance, and then based on the output of the load balancer, we route. And simultaneously, while all that's happening, we also monitor in parallel. That's how you write it in pyretic. It's written once, and it stays the same forever. Now, flipping back to slide number 22, sorry about that. Flipping back to slide number 22, what we're seeing over here is what that actually compiles out in terms of OpenFlow rules. And here they're ordered instead of being priority numbered, but you can think of the bottommost rule as being, you know, priority 6,000, and then this is 500.5.9, and so forth, up to the top rule, which is at the, actually priorities go up or down. Sorry about that. Highest priority, biggest number. Apologies. So top rule 6,000, and then it goes down from there. So these are the rules that you actually get out when you compile it and you go through all the stages of compilation, including shadow removal, which we're going to be discussing a little bit later today. And the key thing I want you to take away from this as we move into the implementation section is if you were doing this by hand in OpenFlow, anytime any of the three previous pieces of logic, the balancer, the router, or the monitor were to change, you would need to calculate an entirely new table from scratch. So you would have to regenerate this thing somehow, and we're going to be going through some of the details of how you actually go ahead and generate that in terms of mechanically, because the pyretic compilation infrastructure and the runtime infrastructure is all mechanical. So there's a mechanically correct procedure for being able to do this kind of thing. We're going to go through the details, but this is what you would have had to do by hand beforehand. And so when we explore the runtime, you're going to be seeing how the runtime makes your life easier by actually doing all of this underlying work for you. You can't get rid of the work. Ultimately, what you say in pyretic has to be compiled down to something, OpenFlow in this case. In the future, maybe FPGAs, but today we're going to be talking about the OpenFlow engine particularly. So what's required is going from a relatively thin runtime that you would have if you were using POX, Knox, Beacon, or another OpenFlow-centric platform to a much more serious runtime that has the ability to compile things, has the ability to keep data structures, etc. So, two key concepts when you're dealing with the runtime that go back to the idea of abstraction. So, pyretic gives you this functional abstraction that lets you say, when I take a packet in, I'm going to produce a certain set of packets out. But it doesn't tell you anything about how mechanistically that happens. Are those packets generated at the controller? Are they generated on the data plane by rules? What's going on there? Well, the mechanisms we have available to us when we're working in an OpenFlow SDN system are two. One, we have interpretation. This is when a packet comes in on the data plane. So this is slide number 23. And we're looking at the top of the two, interpretation. So a packet's going to come in. It's going to hit a rule in the OpenFlow table that says, send this packet to the controller. Maybe all packets hit that. That's the default in OpenFlow. Or maybe just a couple of them hit it. That packet's going to be sent up to the controller. So either on a separate network, a separate control network, or if the control and data networks are converged on a TCP tunnel or some other kind of tunnel between the switch and the controller node, which is represented as just a old school kind of desktop machine over here. Packet's going to go up. It's going to do some calculation, apply the function, and then if there's output, it's going to send it back into the control plane, at which point the packet's going to continue on its way, or packets if multiple packets were produced. So that's way one. That's interpretation. That happens on the controller. The second possibility we have is compilation. This is when we take our policy and we analyze it, and we turn it into a set of rules that are going to sit on the data plane And then, as packets come in, they're going to hit the data plane rules, which are going to realize the behavior specified by the function and send those packets out. So trade-offs here are that interpretation is going to cost a lot of overhead. We're going to have to forward packets across the network. That's going to use bandwidth. Our controller is going to have to handle them. That's going to require computation. There's going to be a delay in all of this, both in transit and in the computation. So we're going to end up really cutting down on our throughput, overloading our controller, and in general making a muck of things if we send too many of our packets to the controller. But the controller has something the data plane doesn't. So the data plane, on the other hand, does all that stuff more or less in hardware, maybe in software, but very optimized software. But it's fast, it's low latency, and it's very scalable in the sense that each switch handles its own traffic as opposed to one or even a few controller hosts handling traffic from many more switches that are being sent to them. So what does the controller give us, though? Well, we can do arbitrary computation. We can store intermediate results. We can do all sorts of things that we couldn't necessarily do in the data plane. So the challenge of designing a language like pyretic is coming up with a set of abstractions and giving them to the programmer that are sufficiently robust to let you do lots of useful stuff, but not so robust that you're shooting yourself in the foot because everything has to go to the controller. And so the design of pyretic is really such that it lends itself towards compilation constructs. Not everything can be compiled, at least not in OpenFlow version 1.0, but most things can. And of those most things that can, not all of them can be compiled into sufficiently small rule sets that they can be deployed entirely on the data plane. Some of them can be compiled, but they'll end up creating exponentially large sets of rules. And Naga has a really nice project about one approach to dealing with this that you can talk to him about later on in the break. But I'm not going to say any more about that right now. I just want you to have, from this slide, the takeaway, two things. You've got interpretation of packets happening at the controller, and you've got compilation of rules that go down into the switches, and then packet handling on the data plane itself at line speed. Okay, so in terms of pyretic's architecture and how we actually create a runtime system that, through a mix of interpretation and compilation, realizes the functional abstraction that the domain-specific language provides, we're going to first start out, and we're on slide number 24 now, with a switch. And this is just one switch in the network. There are many of these, but we're going to focus in on one. Our one switch in the network at the bottom of the slide is a very simple one. It has two ports, ports 1 and 2. Now, this switch is an OpenFlow, basic OpenFlow switch, 1.0, we're going to say, version, and it has a lot of different messages that it can send back and forth to the controller. So we've got port and switch events. So does a port come up, a switch come up, a switch go down, a port go down, something in one of the ports change in terms of the speed it's operating on, etc. We've got packet in events. So packets can be sent from the switch to the controller. We've also got packet outs, where the controller can inject packets into the network to be sent out a particular port on the switch, or set of ports. We additionally have flow modification messages that can be sent down from the controller that change flows in the flow table. And these can delete, they can add, they can do all sorts of different things. And also messages that go back from the switch, particularly on flow deletions, saying, oh, this rule, in fact, has been deleted. And other similar messages that carry metadata information. Finally, we've got things like statistics requests. I want to query all of the currently active rules or some subset thereof and see what are the counter values for these rules. So that's something a controller can send down, or some entity can send down to a switch, and the switch will send back a stats reply. This isn't the full set of things one can do with OpenFlow. You should take a look at the OpenFlow spec if you'd like to see that. But this is good enough to give you an idea of the complexity that needs to be handled by the runtime system. And so the first portion of our runtime system is going to be this thin layer directly above these gray arrows, and that's going to be an OpenFlow backend. It's going to be some piece of code that speaks OpenFlow. So it's able to send out packet outs and receive packet ins. It can send out stats requests and receive the replies. So that involves maintaining connections with each switch. It involves marshaling the creating OpenFlow messages. If they're packets, marshaling and marshaling those packets. So that's our OpenFlow backend. And then on top of that, we're going to build a variety of other modules that are going to be used in the runtime system. So we're going to have a topology subsystem, which is going to, as switches arrive and leave, so these port switch events come, port leaves, port joins, what have you, that we're going to have the runtime and keep a topology that can be used by the various applications that are running. So if I wrote a flood program, I would need to access this topology object, which is kept by the runtime. So second piece, moving over, is the interpreter, right? If a packet reaches the controller, we need to know that that packet is going to be handled correctly according to the current function, high-level function. So what's returned in def main. So when you write a pyretic program, you write def main, you have some stuff, and then ultimately you return some function, some packet processing function, or policy as we like to call it. So whatever that thing is returned, whatever its current value is at time, if a packet comes to the interpreter, it must be interpreted according to that function, and the output must be sent correctly. Now there's also the compiler. The compiler is going to take that function potentially and analyze it. After the analysis, it'll produce ultimately a bunch of flow tables, each one of which will be installed on or update the respective switches, depending on whether you're starting the system from scratch or whether you might have a policy which is evolving in time, and thus causing the flow tables on the switches to evolve in time. Finally, we have the buckets submodule, the buckets module. And what buckets does is it provides all of those data structures we talked about before to support forward and count buckets. So these are the basic components of the runtime system. Are there any questions about that? So Nick first, then.
I have a question on your topology module.
Sure.
How does it work? And what kind of interfaces do you have to them? So
Okay.
we have a lot of questions about it.
Yeah. Okay. So we're gonna dig into the code of that.
You're gonna dive into that?
But I'm going to give you the high-level answer right now. Basically, we represent the topology as a descendant, more or less, of the Network X Python class. This is a Python library that was developed by Sandia National Laboratories and is very widely used. And so we basically use that to encode the network's topology. And you can do various types of graph algorithms over it, which makes it somewhat useful. And there are a whole bunch of other answers to your question, but I'll kind of leave it at that for right now in terms of the topology object itself. Code-wise, there are a couple of ways of accessing it.
To get really specific.
Get very specific.
Basically, we noticed that when you instantiate certain things in mainnet, port numbers are not always consistent. You're probably familiar with this. And so we wanted a basically representation of the topology where you could when you say forward 2 in pyretic, right, it means something.
Yep.
But that
okay, so
might actually differ depending on which time you fire up mininet. So
interesting.
we're looking for a representation of the topology.
Okay, that's independent of
that the programmer could basically.
So I
have POX, it's LGP.
Yeah.
So discovery.
So I would.
We were trying to dig that out of pyretic.
Okay, so we'll dig into that. We'll dig into the actual code on that. I think that's probably a bug because we're supposed to.
It is a mininet bug.
Oh, well, no, but it also might be a pyretic bug. Like we should be able to handle that. And if our topology detection code is not where it should be, it's one of the things on it would be great to have somebody work on that as a semester project. But
I'm happy to show you what we did with overflow discovery. But then the other thing is and maybe you're not intended. Maybe you're not supposed to do this. We couldn't figure out the data structure for topology.
Okay.
And then we tried to actually run overflow discovery,
Okay.
So we figure like it's running on POX, right? This should just work, but it like actually didn't.
No, it's going to break because basically the way we do it, Jen, is we actually do the discovery, and we'll dig into the code after. But basically, what we did was we took a very similar. We looked at the POX mechanism for doing discovery. We tweaked that in a variety of ways, and then we implemented that in pyretic as opposed to in POX because we wanted to be relatively agnostic to POX. So it's surprising that it doesn't behave the same way as POX's topology detection.
Basically, the data structures are a little bit different. Like
the data structures are a little bit different.
Like,
that's true.
I mean, we can dig into it later, but like,
yeah.
What we did with POX is discovery stuff, and kind of there, but it's really hard to.
Yeah,
so we just
and it's not nearly as well documented as it should be. So.
This was the one. Pyretic was just actually.
Okay. I would expect it to use the same port numbers to discover the same port numbers as POX. But.
So the issue here I have like. Actually, the topology, like people kind of like explicitly expect like the order which you add
oh, yeah, you can't assume that.
First of all, that doesn't actually guarantee that.
And, yeah.
So you write your code assuming that like you're in some surprises. And the other thing is.
Okay.
Even if it did that, it's like programmatically bad because like someone could go in and like change the meaning of the controller. You're assuming that. So
yeah.
It just seems like a really like bad thing to depend on anyway. And what I wanted was to extract the topology.
Okay.
Later, like, bottom line is like people would wanted to write stuff, report out on this report, this thing, without a clean way of extracting the topology.
Okay. So actually
gave up.
I think this will be really good to do right now. Actually, I'm going to do a quick.
I didn't mean to derail your presentation.
No, not at all. I mean, I think this is an important point. So let's give it a little bit of attention right now, and see if I can actually figure out how to share a. Oh, there it is. Okay, so for those of you who are remotely, I'm now sharing my web browser with you. And if you want to join, you can. It is not on the screen behind me, because I'm not doing mirroring, but I will just move it there. Assuming I can. Okay, so let's get this at the right thing. And I'm just going to turn myself a little bit. I'm just going to do a Google search for pyretic. This is the easiest way. So we're going to go to the GitHub repo available through the page. We're in Legend Master. So top level over here, basically, this is all the stuff that's pyretic itself is in this subfolder of pyretic. But there's a lot of other goodies, some stuff for doing mininet automation, the OpenFlow client backends that you saw in that diagram before, pyretic itself, of course, some Vagrant stuff. So if you want to create the VM using Vagrant, you can do that. Some makefiles, readmes, all that kind of good stuff. And finally, a pyretic.py program. So this is actually the script that gets run, I think. Yep. Okay, so now that we've dived into the core of pyretic itself, or the subcore of pyretic, the core is actually the core. But so what we're looking at over here is, hey, this is really what's going on, and that's going to be where we spend most of the rest of our time today after the slides, or at least in the session after the slides. But there's also some back-end code, which is sort of, if you think about in the diagram we saw before, you had that thin OpenFlow layer. So that's the OpenFlow client, it's outside. But that thing communicates with something on pyretic side that basically takes all that gunk and just pipes it back up. So this is what communicates with that thing. we might eventually integrate it all, but right now, the reason why this exists is because our OF clients are actually like POX or Floodlight, or you could write, something else. I think there's a project where they've written a bunch of folks. Maybe one of the folks who's hanging out online, in fact, has done that. But what comes in the official distro is just a POX version. We just reuse all of POX's stuff, and then we create a connection. I think right now it's just a Unix socket between the Pyretic backend and the OpenFlow backend, the POX client. Okay, so that's what's going on in this backend over here. We got a bunch of libraries, good stuff, which we'll go through. So these are things that you can use on top of Pyretic. We've got some modules. What?
I have one other question.
Sure.
I'm sorry to interrupt you.
Go for it.
Just when you started talking about the backend stuff,
Yeah.
a question came up. So like, when people sort of like talk about the performance of these controllers and stuff, like certainly the issues of like POX, are always so like, but now when you talk before about like interpreter and compiler, suppose you had a different backend.
Yep.
Like something with C or
yep.
whatever. Okay, so your compiler might be I mean, your compiler might be eventually, compiling rules to the switch, but now your interpreter, like, it's going to still be in Python, I guess, like, because if you got Pyretic, the language, right, and then you've got a backend which is in like something else. Where do the packets go when they're interpreted, right? It seems like they'd still come up to Python. Like, do you? Does my question make sense?
I think the point you're getting at totally makes sense. Basically, if I'm going to boil that down, I'll say it like this: you're asking in terms of the performance model for Pyretic and how efficient that is, and how compared to say other systems, and how we might make it more efficient. Would that be roughly the space that you're exploring?
Yeah, I guess the problem statement I was thinking of is like, can you keep the syntax of Pyretic and have a faster runtime?
Yeah. So the answer, yes, you can do it. We haven't done it yet. In terms of specific things that you could use to do that, so one is the current backend is in POX. It's not highly performant, and doing this Unix socket is not the best way to do it. I'm currently looking into if we keep this tiered architecture where we build on something else. Well, one, we might switch over to a much faster OpenFlow backend. Something written in C++ that uses multi-threading, for example. The folks at Stanford have a really performant version that they managed to hack up. I don't know what happened to it, but I know the folks who did it, so I can talk to them. So that's one. Two is, I was actually thinking if we do keep that structure, we can switch over and use something like Thrift to do the connection between the backends and do memory mapping. So that way it perhaps is a bit faster. Then when you get into the Python code, when you're doing things like in terms of interpretation and compilation, things which are potentially compute intensive or latency sensitive, you can actually use Cython, which is a library, a restricted syntax of Python, which compiles directly into C. And then you can basically, so what you do is you instrument your code, you figure out where the slowdowns are and where the critical computation points are, then you rewrite those in Cython, and then you get the C performance, which is actually going to be faster than your C++ performance in general. And there are a variety of other techniques that I would really like to see ported to the runtime system. Another path, which is compatible with the Cython approach, doesn't actually rely on using some other OpenFlow backend. It would actually be, let's replace the OpenFlow backend with one of our own that learns from previous designs and also does those things quickly that Pyretic needs to do quickly, because Pyretic is very much more focused on efficient rule installation than, say, a lot of these other controllers, which have focused on being able to handle a huge number of packet ins. That's generally the evaluation point for controllers. Possibly because switches are so bad at handling flow mods and installs That's the only way you can like get a CPU saturated right now when working with OpenFlow is just to, have the switches send all their packets to you. But it's not very realistic or useful, in my opinion, when you're dealing in a model like Pyretic. So that all said, I'm going to now answer your other, and then we're going to come back to what we were talking about before, and then we'll dive back in, perhaps after a slight break. I don't want anyone's brain to explode. So we got a whole bunch of stuff in here, but the thing I want to show you right now is examples. And so examples has a bunch of, examples, things that show you how Pyretic, little bits of how Pyretic works. And so the one that I'm going to, we're going to look at right now is the topology printer example. This will just give you a little bit of user level how you can use the topology. And then we'll, dig into this, one, this has its shortcomings, which it can be better. And two, we're going to actually go into the code that supports this and show you in the runtime how this all bears out and happens, how we learn the topology, how the topology is stored, what the format is, all that. And, maybe someone will even volunteer to write some documentation on it. That's better than what I currently have up. And we can go through those docs too later. But for right now, let's look at topology printer. So we go to the top over here. We've got, basically, we're just doing the core and the standard libraries. And how does the topology printer work? Well, it's a dynamic policy. So if you want to access a topology object from the runtime, you need to create a dynamic policy. Because static policies don't care what the topology is, since their behavior never changes. So the convention we've adopted in Pyretic is if you want to access the topology, if you want to do something that cares about the topology, cares about change, it needs to be done using a policy or a packet function which descends from the dynamic policy. Okay, and this particular dynamic policy starts off by setting its topology to none, setting its lock, creating a lock, and emitting just like a regular dynamic policy. So it's basically a dynamic policy that happens to have two new variables. These variables are used for storing the topology and printing out the topology. So set network. This is the next. This is the important method for topology. So every dynamic policy, whenever the topology changes, if that dynamic policy is part of the larger policy that's running on the runtime system at that point, the runtime system will know it and will notify that dynamic policy, hey, there has been a change to the network topology, there's been a change to the network, and the way it does that notification is by calling the set network method. This is a method that's defined in dynamic policy, and what we're going to do is we're going to override it. So we override it, and we say, okay, well, first, wait until we've got the lock, because we don't want to, if we get two topology changes in quick succession, somehow print out a garble of their two results. So we're going to grab a lock, and then we're going to do a little test. So, if the topology exists, so if we've set this for the first time, because this is just a variable we declare, self.topology equals none. So if this is true, if it's previously been set, and it's the same as before, then, because the runtime can sometimes give us a couple of topologies that are in a row that appear to be the same. So if this is the case, then we're going to just skip. Otherwise, what we're going to do is we're going to print out self.topology by just going print on it. We're also going to print the network topology. So this is printing the previous value that we had stored. This is printing the network topology. Now we're going to set self.topology equal to network topology, and we'll print self to see that we updated correctly. Yep. And if self.topology is none, well, this is going to evaluate to false, so we'll go over here, we'll print out none. And the new topology will sign it, and then we'll test to see that our set is correct. And so this is how you can print out a topology. It's also an example of how you can access the topology object and do a variety of different things to it. So, instead of doing assignment or doing printing, you could do other stuff. What that other stuff is, we'll see a bit more of when we look at the code for the topology object. and also looking at the topology object's print method or toString method, underscore underscore str underscore underscore, will give you at least some idea. I mean, that's the ultimate piece of documentation, although definitely not the most accessible one. But it tells you exactly how you translate a topology into a string representation. Any question? Gene, you were raising your finger? Okay, cool. So before we go and get there, I'm gonna pull back, and we're gonna go back to the slides and kind of run through a little bit of higher level stuff. Not really higher level, but a more abstract representation than the code itself. So that way, when we dive into the code, we will, you hopefully won't be too disoriented. Any questions from the audience here or out there? Okay, so I'm going to switch back to the slideshow now. So for those of you in the audience, we're back to slide number, in the internet audience, we're back to slide number 24, systems architecture. So this is our runtime, as we've seen. We've talked about it a bit. Question, Naga?
I'm just wondering, the buckets, is that the right place for buckets? Or is that aren't buckets the language feature? So you don't have a runtime component for each language feature.
So okay. So the runtime system itself doesn't define the language. The way we have it is if you go, and actually now we'll quickly go back. And for those of you, you're now looking who are remote, we're back on the GitHub website. It's being screen shared with you, hopefully. So what we're going to do is we're going to go to core. We're just going to quickly go over what's in core. So in core are the following. There is the language, which is the definitive definition of pyretic, the DSL, and the dynamic features. We've got some tools that let us do things to the language, and we've got some classifier code which defines what a classifier is and provides some definitions and some other helpers for the compilation process. In fact, perhaps quite a bit of it. We also have definitions for what a packet is and what the network object is. So, in fact, let's click on network object very quickly. I said I wouldn't do this, but I won't. So if we go down a little bit, we'll get to location, and then we get to topology. Okay, so a network is an object one of whose fields is topology, and topology is itself a version of network X graph, or descendant thereof. And so you see we've got these equality testing methods. We've got adding switch heading, port setting links, egress locations, interior locations. So this will take the topology object and actually figure out, okay, what are the switches and ports that are on the very edge of the network.
This is one thing that,
yep.
I can't remember what discovery that it built. Just trying to figure out which switch port goes to a particular host with a particular name.
Yeah.
It's real tough, actually.
So I can tell you how to do that's a Mininet thing. Yeah. More than so pyretic has no knowledge of the hosts because we only get information from the switches, and the switches don't know.
Right.
So you literally,
same
yes, you cannot, you can't do it that way. Yeah. There are things you could do. You could build a pyretic program that would say, potentially send out probes on all the egress ports. Yeah. If you configured the host to respond to them properly, you could, potentially do that kind of thing. But you can't. OpenFlow doesn't give you the tool you need to do what you want to do in and of itself. You'd need to have some kind of script or daemon or something running on the host that would respond to some kind of probe message. And then you could create your own probing engine. And you could do that using OpenFlow-based tools and therefore using pyretic. But anyway, I just want to go down so we can quickly...
can you remind me too,
right here.
I forget,
line 410.
So
yeah.
You went through add, switch, add, what I think. What calls those in this thing?
The topology detection module. Topology detection, and the topology detection takes place in the runtime. So, as we'll see a little bit later, the runtime instantiates a new network object, and that new network object has a topology object associated with it, and the runtime conducts topology detection as one of the things it does, and updates the topology object belonging to the concrete network object, which exists. And that concrete network object is attached to the runtime. And we'll see how all of that works, but at 410, if you want to see how we take a topology and turn it into a string representation, well, this is exactly the code that does it. Should I go through this quickly, or should we leave this to later? Because I don't want to get into the weeds.
I'm sure like probably not everyone's interested in this, but I'm actually I'd be interested in a deep dive session.
Okay.
Actually.
Okay, so we will do a deep dive on this, perhaps in the afternoon, because I know the folks from your.
I just have a high level comment here.
Sure.
That, like, one problem I have with the class here is that, like, when I have to look at it, printing out a string representation, to figure out like how to.
It's bad. I take that.
Trying to reverse engineer like which functions I should be calling to get.
Yeah, I totally own that. We do have documentation, which I'm going to pull up right now, just to see exactly how lame it is. I'm sure it's lame. You know, but how lame, I'm not sure.
I mean, I'd be willing to work on this myself.
Yeah.
I think we have like really uses.
So first thing, I'm just looking at the tutorial. Okay, the tutorial isn't telling you anything useful. So that's number one. That's bad. Now let's look in the documentation over here. Let's see exactly how not impressive. So this is not a good way to look at the documentation. Language. Oh, let's look in here. Okay, so yeah, so you've got an abstract class for networks. That's really helpful. You know, I mean, I'm not, you know, I deserve this. I have not come through on what I should have done. Let's look at this core language. The language is nicely documented. Hey, look at that. So, but yeah, it looks like the documentation for topology is really like terrible. So, my bad. And we'll work on getting this better, and we'll take time later today to really, you know, dig in, and at least we'll have some video documentation of
that. Yeah, I'm happy to help on that too. Like, I think there were several things where we had to kind of shit like topology.
Okay. Remember, if you're ever like at a point where you're getting frustrated, like even mildly, don't like spend like a week on it. Just call me on the phone, you know, and be like, Josh, you're a bad person.
I think we just spent like a few hours.
Okay. Because AT&T's promised me like, you know, time to be able to, you know, do some pyretic stuff. So I expect them to let me do that. So anyway, we're okay now, folks. Yeah. Before moving on.
Yeah. So you mentioned like if the topology detection is a part of the runtime.
Yep.
And then you get response.
Yep.
My question was like, where does the spanning tree protocol and these things, are they a part of the runtime, or is it something?
Spanning tree. So there is no spanning tree protocol in pyretic. Pyretic just collects the topology. Then, because we're using this great NetworkX library, we have a whole bunch of minimum spanning tree algorithms which are provided by it, which are computationally efficient and, you know, well tested and all that good stuff. So you can run Krishkal's, you can run Dijkstra, you can run all sorts of.
You can run the pyretic application like as a user. I can use
Yeah. You can take that topology object and you can like literally. Okay, so one more thing in code I'll show. So now we're going to go back past my really unimpressive documentation to pyretic core, and a great way to see how we use the network. Oh, sorry, it's actually in language.py, because we provide flood as a prepackaged thing, right? And so if you go down and you, where are you, flood? I've went too far.
1088.
1088. Oh, I haven't gone far enough. Isn't there a song like that had that lyrics? See too much. Whatever. Anyway, 1088 DexGen. Flood is a dynamic policy. Flood keeps, guess what? A minimum spanning tree. Internal representation. That's initially none. When set network happens, we check. We set a thing and changed. It didn't change. If the network's not none, then we're going to do some stuff. What are the stuff we're going to do? What are the things we're going to do? It's possible to get a none network, or at least it was in previous versions. So this is, it's worth doing a check, even if it's just, an assertion. So it's in the code. So what we're going to do is we're going to take the network topology, and then we're going to run minimum spanning tree on it. Topology, right, descends from network X. network X provides minimum spanning tree. So we're just accessing network X's minimum spanning tree on a network topology. And now we've got this thing. And, well, if the MST is not none, and the MST, so if our old MST is not none, and the MST is not equal to the updated one, then we're going to update it and we're going to say it's changed. If the MST hasn't changed for some reason, maybe the network changed, but our minimum spanning tree didn't change, well, then we shouldn't change anything. So we're not going to bother to change anything. Otherwise, if MST was none, then, well, of course we're updating because it's the first time we're calculating the minimum spanning tree. Then finally, if in fact we have changed, then what we're going to do is we're going to generate a new policy corresponding to this minimum spanning tree. And this gives you another look at how you can use the network topology. It's not great documentation, but it is correct. And basically what happens here is we create a parallel policy, one for each switch. So we match on a switch, and for each switch, we do a parallel policy where we map this cross-forward thing, X forward, to the attributes, ports. So over here, it's a list comprehension. So basically, we're looking at every node in the minimum spanning tree where data is set to true. So this lets us access the data members. So we get a switch and a set of attributes, those data members. And then basically, we take the ports of the attributes. And these are actually, ports is a dictionary that maps from a port ID, an integer, to a slightly more robust description of the port, which we don't need for this purpose. But basically what we do is we get all the ports out, and we just take their keys, which are the integers. So now we've got a list of integers, and we're going to map cross-forward across that list of integers. Cross-forward is a pyretic policy that's provided out of the box, which does the same thing as open-flow forward. So it basically matches and checks that it wasn't the same port. So whatever port you're forwarding out port 1, it does a match not in port 1, sequentially composed with forward port 1. Make sense? Okay. So basically we map this cross-forward across all the ports for that switch. And we parallel compose those for all switches. And then we've got, well, forwarding on the minimum spanning tree because we were using the self-MST. If we had used a self.network, then we'd be sending everything out, on every port, and we get loops, and it would go crazy. Okay, so, a little more color and flavor. Let's go back to the slides now. Okay, so for folks who are watching at home, we're back at. Oh, one more. Sure, go for it.
Just like I noticed, like some earlier examples, like even last year, you had to call set network to do certain things.
Yep.
Is that still the case? I don't see that in some of the more recent examples. Does that mean call like automatically? Just not always necessary.
So the cases where the only cases where it's necessary for the user to call set network is if they want to do something based on if they want to extract information from the network topology.
So for example, I want a topology that might need to call set network.
Yeah, you're going to need to call set network.
Self-MST variable might actually
be. Yeah. So if you're using flood, so you could create a dynamic policy that descends from flood. So you could actually create a policy that descends from flood, your flood, and you could, in your flood, change around so you could print out the MST. For example, or you could just, create your own like printer and, do the MST calculation.
Just one other question about the structure of the thing. So like dynamic policy basically has this variable network, I guess.
Yeah, here we'll take a quick look at.
Here's my question.
Yep.
Do you need to basically be using a dynamic policy to get the topology?
Yes.
Okay, that was my read of the code.
That is what you need to do. That is the definitive way of getting the topology. Now in query library, like you can create potentially a helpful method that lets you do that. The example is actually kind of a prototype of what that would look like, but I decided that it was already poorly documented, and I didn't want to give you 2 ways to do it yet until it was better documented.
Okay. That was kind of how I read it, but I was sort of not sure I was reading it correctly because I was like, well, why shouldn't I be able to why should I have to use a dynamic policy to get a topology But then that was sort of how it was.
Yeah. So another reason why we do this is because we had virtualization functionality built into an earlier version of Pyretic. We've right now deprecated that because there were some technical issues with it. It's in the process of being revamped, but ultimately, we hope to allow you to create virtual networks and have policies run on those virtual networks. And so when you access a network, if you try to just access the network in Pyretic, and that's what we give you by default, then, well, which network is that? And how do you access all the other ones? And what's the right API for that? So we decided better to access it through the policy for right now. And
oh, okay, just in case you want to pass a different technology.
Exactly.
So that, to be clear, like that functionality doesn't quite exist.
It doesn't. Yeah, it doesn't quite exist.
But that actually would be okay. So
but I didn't want people to get used to doing it a different way and possibly even make the code depend on that. That would then lock us in when we do ultimately, hopefully, bring back the virtualization stuff. And the virtualization stuff is, yeah. So I'm trying to plan ahead, yeah. But it definitely makes for a clunkier interface, especially given the complete lack of any reasonable documentation on my part, which will be rectified, possibly by you, Nick. So now, any more questions?
One more.
Okay.
So this thing also present in the forward policy. When you forward to port 1 or 2, there's an internal spanning tree running below that.
No. When I say forward 1, it literally just changes the output to 1. And then that's passed down to the runtime system. And then the runtime system does some stuff with it. And one of the things the runtime system will do, as we'll see, is do a check on the actual topology to make sure that port's there. Right. At least it did. It should, in most cases. Hopefully in all cases. I don't know. I haven't stress tested that part of the code recently. So, okay. No one's allowed to ask any more questions right now. We're going back to the slides. For those at home, slide 24, system architecture. Okay, so we have our switch. We have all the open flow junk that it communicates. We have our OF backend currently written in POX. This OF backend, actually, if we wanted to break it up, is actually 2 boxes. 1 box, which is the POX client. And then there's that socket, and then the top box, which is the pyretic backend. And the pyretic backend talks to the topology, the interpreter, the compiler, and the buckets modules. And on top of all of that runs your lovely program, written in Python with Pyretic's additional syntax. So let's take a look at one of these. Well, this is all inside the main method up in the top bit, this green stuff. So we've moved on to slide number 25. So let's say we wrote a main that declared a bucket, a new forward bucket B, and registered a callback with that forward bucket to print out the packet. And then return the following policy. So this is an if policy. If we match field f equals v, then we're going to forward out port 1. Otherwise, we're going to, in parallel, forward out port 2 and send the packet to the bucket. Make sense? Okay, great. So how will this actually work? Well, let's say we look at a packet that's coming in, and at home, guys, you can follow this animation step by step. We see on port 1, we have packet P, small little brownish box. And I'll let you know something about P, namely its field F doesn't equal the value of A. So it's going to be going into our flow table. And if we look at the flow table, we see 2 sides. One's going to be the match side, the other's going to be the action side. And we've only got one rule, star, match all packets, and forward to the controller. So this is shorthand for that hexadecimal that we saw earlier. So when our packet comes in, boom, it is going to get forwarded to the controller. So it's going to be turned into a packet in, sent to the OF backend. It's going to get into the OF backend, and at some point it's going to get wrapped, and it's going to get turned from a regular packet, a concrete packet, into a pyretic packet. And we'll see exactly where that occurs in the code. And the pyretic packet has some metadata. For example, the import is 1. It also has some other metadata, which I'm not showing you. But this is the most important part of the metadata for this example. And we're just looking at how the interpretation works. So When we go into the interpreter, once we get up here, we're actually on the controller node. So we've gone from the data plane to the control plane, over the control network, or tunneled across the data network, and we're literally running on that server machine. Okay? Anything that happens to the data plane has to happen in this gray box at the bottom. So the OF backend is now going to hand the packet off to the interpreter. The interpreter has a pipeline, which we're going to take a look at in the code a bit later. But yeah, but it would be bad for the people there. So I got some chats. Share slides. Somebody muted me. Okay, so guys, the reason why I can't share these slides with you is because with the setup we have, the slides themselves will show up on the projector screen, and the presenter notes will show up on my desktop, which is what you'll then see, which is not useful. If I swap displays, then all the folks sitting in the room can't see what I'm doing. Although I guess over the break, I'm going to see if I can come up with a way around that. It might involve not using the projector at all. But for right now, yeah, you just need to download the PowerPoint slides and flip through with the animations. And I will, I'll do my best to see if we can resolve this when we take a break next. Okay, sorry about that. Okay, so back to this animation. So we get a packet that comes in, and this packet is going to actually go into this function and be evaluated, just like those evaluation rules we saw at the beginning of the talk. So, you know, first the packet's going to go in, and it's going to either match F equals V or not, and then depending on which of it matches, it's going to get sequentially piped to forward 1 or to B plus forward 2. And so in this case, the packet is not F equals V, so it's going to go B plus forward 2, and that's going to produce two packets. One whose output is 2 on the switch, and one which we'll see in a moment. So the one whose output is 2 will go through the interpreter to the OF backend, then out into the switch, and out into the network from there. Meanwhile, our second packet, which is import is 1 and B, so this packet is now tagged as being as going to a bucket. That's going to get passed by the interpreter of the bucket engine, placed inside bucket B, so now it's in that data structure, and then at some later point, based on the semantics of bucket B, print packet will probably get called back on. Question. And then the packet will be thrown out.
This is because it's parallel. What is this sequential?
So well, what does forward bucket do in the data plane? What does it output? Empty set. So if you did sequential, then you would just throw the packet out. It would be like dropping. Okay, so this is interpretation, which is all well and nice, but
what is it mean for a packet? What is that?
Oh, so there's literally, you know, something.
Is that like a
that exists?
Or
what?
Is that like a hash table? Or
yeah. So it's a little more complicated than that. We'll go into the details in the runtime.
The packet's like sitting there on the controller in memory or something?
Yeah.
The whole packet.
The whole packet.
Okay.
If you use a forward bucket. If you use a count bucket, no, not necessarily. Yeah. It might be just a count. Depends. But we'll get to that.
Give some applications.
Oh, forward bucket, like Mac Learning is a good example of using forward bucket. You know, likewise, if you're doing a stateful firewall, you probably want to use forward buckets at least some of the time.
I guess one question would be, what makes that packet go away?
Yeah. So basically, the current semantics for the forward buckets go like this. you register all the routines you want to handle that packet, and then there is kind of a separate loop that after all of this happens, doesn't interfere with the main processing. At some safe point, the bucket will be evaluated by all the callbacks and then thrown out.
Are your queries like packets and bytes? Are they just wrappers around the bucket?
Yep.
Okay, now I understand.
Yeah. So all the queries are just boil down to
they're just buckets.
Packet buckets and forward buckets in parallel, in sequence, with various predicates that may dynamically change over time.
That's why I haven't seen this or used it.
Yeah, if you use the wrappers, and we've been working on the wrappers, new versions very close to being released. And we might go through some of that code later, maybe tomorrow. I don't know. We'll see. So this is interpretation, and interpretation is the process that happens, just when we have a packet that comes into the controller. But pyretic does a bunch more than that. If it just did this, it would not be very performant at all. So we have all this compilation technology. Let's leverage it. How does that work? Well, same policy again, but here, no packets arrived yet, so the controller has some spare time. It's going to take this return policy, and it's going to throw it into the compiler. And we're on slide number 26 for those folks at home now. And basically, the compiler is going to produce an intermediate form called a classifier, whose left-hand side are open flow matches, but whose right-hand side are actually not quite open flow actions. They're a hybrid. They're actually reduced syntax in pyretic. Is the best way to think about that. And so this classifier, comes out. It gets optimized. It gets turned into multiple ones for each switch in the topology potentially. Gets optimized again, and then it gets installed, i.e. pushed out to the switches. So now we've got these rules in the data plane. If f equals v, we're going to forward out port 1. Otherwise, we're going to forward out port 2. We're going to do some modifications, which I've left unspecified, but they're going to effectively tag the packet in a way the controller can recognize, and then we're going to forward it to the controller.
So, compilation function has something to do with pyretic, or it will be proactively compiling the rules?
Yeah, this is proactive compilation. So this is basic proactive compilation. We analyze the policy, we turn it into a complete classifier, and then turn that into a bunch of rules that get installed on switches.
But in the case of backlining, when you're reading a packet from the forward bucket, you're compiling this policy again, right?
Yep.
Then you're doing it dynamically.
So there's the issue of recompilation, and there are a variety of approaches to recompilation, and some of the stuff that you did was, I think, on that. We'll talk about recompilation after we've kind of covered compilation. So we've got our data plane rules installed. Our packet comes in. What's going to happen? Well, it's going to get forwarded out port 2. Great. It's going to get modified and also forwarded up to the controller. So now we've got one packet that went out in the data plane, line rate, another packet that's in the back end, and it's been tagged with this bucket tab, which the controller can recognize. And why is that important? Well, we're going to pass it up to the interpreter next, and it's going to get interpreted by our policy. What we don't want is that packet to create a second forward bucket packet that then gets sent out into the network. We don't want two copies going out. That defeats the purpose. So what we do is, because this has particular bucket flag, we change the way evaluation works slightly. So that way we only produce one bucket. We only produce the packets that are going to buckets, not the packets that are going back to the data plane.
And you're using some specified fields, like VLAN or something to do that.
Yeah. And this allows us to disambiguate between the case when we didn't get to install the rules yet, and the packet had just come in before we installed the rules and went up to the interpreter and needs to be forwarded out, versus the situation where the rules are installed in the data plane, and we don't know exactly when they're going to be installed because we're the controller, so we can disambiguate using the tag. No, this particular example right now that I'm showing you is not one which is currently in the released code, or actually I'm not even sure if any of the branches right now have this. This is kind of something I want to code like the next coding day I have. Although if anyone wants to take it on, but it's a pretty straightforward optimization. Although there are a couple of like little complexities in it. But this gives you the idea of how interpretation and compilation play together. And that's really what I want you to get out conceptually before we jump into the runtime. So this is not a definitive description of what the runtime is. This particular slide is aspirational for the runtime, but it gives you the exact idea that, hey, compilation and interpretation are not only need to produce the same results, but they actually interact with one another, potentially in a variety of ways in the runtime. And we may see some more of those. In fact, I think on the next slide or two we will. So if packet goes to the bucket again, we're good. But we didn't take any latency hit on the data. So actually, here's another situation where the compiler and the interpreter are very much interlinked. And so this is a compiled count bucket. And basically what we did was we said, hey, C is a count bucket, and we're doing the same policy as before. If we take a look at what's in the buckets right now, we have C, and it has numbers for the number of packets and number of bytes. And it also lists the rules on the switch that apply to this bucket. So the rules that have items that need to be counted. So in this case, the star rule, but not this rule. This rule is not going to be counted. So we got a packet. It goes through. Well, the switch itself is going to update the counters in the hardware, and then those are going to get transferred to the software. And periodically, what our count bucket is going to do is it's going to send down questions for the rules that it needs counts on to update. And it's going to get those results. And it's going to be able to say, okay, bucket C has these number of packets and these number of bytes.
Does the compiler somehow know the switch?
So this is basic. This is OpenFlow 1.0 standard.
Okay.
Although I'll note that Naga actually ran into this problem. The counter as reported by OpenFlow implementations may be not accurate at all. So the number of packets, right?
Not sure if that is I don't know. It could be a switch from there.
Well, but that's the thing. When you get at the OpenFlow level, you have this OpenFlow switch. The OpenFlow switch itself as an OpenFlow switch gives you the wrong information. The interior Broadcom ASIC or whatever is going on in there probably gives you the right information. But they've just messed up the implementation. But we're interfacing with OpenFlow level stuff, not going lower down. So we're subject to all the limitations of OpenFlow. So if we get bad counter values, there's not much we can do about it, except potentially give out warnings.
I guess
we know based on the switch. The switch is.
I guess what I was sort of like here's another example. OpenFlow doesn't you might say average or something. Right?
Mm-hmm.
Okay, well now you've got to know that the switch doesn't support doing that in hardware, or maybe it does, right? So like,
average is really easy because with count buckets, assuming that it gives you the correct counts for these two, you just divide.
Yeah, my point wasn't specifically about average, but
okay.
More like about the capabilities of the hardware.
Yeah.
And like what your compiler has to know about that. Like.
So right now we assume just kind of 1.0, nothing more. Now you could imagine creating extensions for switches where you provide information, or do a variety of smarter stuff. But that's not. We're not there in the language design, in terms of language design or anything like that. Yeah, that's kind of farther out stuff.
Which part of the code does it?
Yeah. So some of the compilation. So the compilation itself is done by the runtime, and and some of the methods that are used by runtime.py are defined and classified.
Okay.
And we'll go through compilation in detail after we have a break, but. Oh, okay. Before we do this, so slide 28 for the folks at home, just something to kind of think about in terms of this. Well, what happens if I had a packet that came into the interpreter while these rules were getting installed? How do I handle that? Well, the interpreter is going to pass the packet to the buckets and then update the counters on the bucket for that one packet, and then it's going to subsequently take the results by this and add them. So we started out with 0, 0, but you could have started out with 12 and 126 or whatever it is. And this comes into our very next slide, slide number 29, about staging updates. So if we've got a dynamic policy whose behavior is changing, well, we might get, say, a query that is connected to a bucket that returns something. So maybe we're doing MAC learning, maybe we're doing a stateful firewall, or topology change that impacts the dynamic thing, or maybe something just from anywhere. So any of these can change the dynamic policy. When the dynamic policy changes, the runtime finds out immediately. And I'll show you how that works. And so then the runtime is going to update the interpreter loop to reflect this at a safe point. It probably is going to need to wait until the packet processing pipeline that's currently in process empties. And then it's going to also update the compiler. So it's going to do a recompilation. Now, in the course of that recompilation, it's going to potentially be doing a bunch of modifications to the flow table, some of which may include deletions. Now, if we're deleting a rule whose counters we were using for a query, well, then we're going to need to carefully monitor the flow deletion that comes back and use that information to update the buckets, the count buckets that might be affected. So again, this is another place. And this actually is in the code. Or at least it's in a branch that's going to be released very soon. A branch that's available publicly and is probably going to be ported to the main pretty soon. Some of it may already actually even be in there in the main. But anyway, we'll look in the code and we'll see. But so this is another interplay between interpretation and compilation. Does that make sense? Any questions? Okay, cool. So now let's just walk through a quick compilation example. And we are now, for the folks at home, on the slide after 29, which doesn't have a slide number. And what we're going to do is we're going to look at actually that policy we were looking at before, a simplified version of it. So this is if matchf equals v, forward 1, otherwise forward 2. But this is written just in terms of the Python primitives. If underscore is itself a derived, it's just syntactic sugar, more or less. And what it means is matchf equals v, sequentially combined with forward 1, and at the same time, don't matchf equals v, sequentially composed with forward 2. Does that make sense? Awesome. So how are we going to take this then and turn it into something that can actually be run on the switch? So the way in which pyretic and frenetic OCaml approach this particular compilation problem is by the following technique. We have a limited number of primitives. Each primitive has a provably correct classifier that represents its behavior. We then show for each primitive classifier, or rather we show for given any two correct classifiers that if you parallel compose them, you do a certain mechanical thing and the output is correct. Likewise for sequential, likewise for negation, where negation makes sense. And thus, by induction, we can prove that all compilation is correct. Not necessarily efficient, but correct. And we'll talk a little bit about efficiency in this simple example. So what are we going to do? We're going to break our policy down into an abstract syntax tree. So we've got leaves here. Each leaf is a primitive pyretic policy for which we can produce a known, provably correct classifier. And each interior node is some operator in terms of composition. So negation, power, sequential power. Okay? So let's go in from the top. And we're going to do a traversal of our tree. And we're going to evaluate our nodes first, and then we're going to come up and evaluate interior nodes. And when we've evaluated all of the descendants of a node, then we can evaluate them. So first node, matchf equals v. So this is our classifier. This isn't quite an open flow table yet, but it's on its way there. So we've got our open flow matches f equals v, goes to ID. This is not something that exists in OpenFlow. It is something that exists in pyretic. So match f equals v. We're gonna, do our ID thing, which is pass the packet through. If it's star anything else, then we're gonna drop it. So we're gonna produce the empty set. Okay? And you can see any packet that matches f equals v will hit ID. Everything else, the remainder will hit drop. So we're good. So now we're gonna hop to forward 1, and guess what? Match all packets and forward out port 1. This is not the OpenFlow action yet. This is the pyretic policy forward 1, or something very much like it. But this is a classifier now. And now we can come back and we can do a sequential cross product. So basically, whenever we combine 2 or more classifiers, well, we'll think about them 2 at a time. Basically, what we do is we take a special type of cross product in each case.
Can you explain when you say classifier, like is that just like any one of these?
So yeah, so these things are all classifier. A classifier is a table, but it's not an OpenFlow table. It's a table that has OpenFlow matches on one side and a subset of pyretic policies on the other side in parallel. That's its definition. The technical definition is slightly more complex.
In parallel,
Yeah, in parallel.
In parallel with what?
In parallel with one another. So if I had ID, comma ID, that would be ID plus ID. Yeah, and we'll see one of those momentarily. Let's go through sequential cross very quickly. So I'm flipping through the animation for those of you who can't see, and I'm sorry about that again. So what we're going to do is we're going to take the first row on the first table and the first row in the second table, and we're going to combine them together according to the sequential logic. The sequential logic says that if we have an output from here, from our first row, that can match our second row, then what we're going to do is we're going to okay, it's not me. Good. I thought maybe somebody from home was calling. So what we're going to do is we're going to create a match that matches the first rule, because obviously the first rule is not matching anything else, with the action of the first rule combined with the action of the second, sequentially. And we know ID sequentially combined with forward 1 is just forward 1. So now we've got our first rule. Yeah.
So is the mathematical thing there like a set intersection?
Yeah, well, it's the set intersection of the output of this.
The output of one.
Yeah. So if this had been a, modify f equals to j, then then we would have needed to account for that. So then what the output here would be f equals v, mod f equals j,
and then the intersection.
And then forward. Yeah, well, potentially. I mean, so if this wasn't star, but this was f equals j, right? Then you get forward 1. Yeah, well, you get forward. Yes, there are a variety of roles, but we're going to go through this kind of simply, and then when we get into the code, you'll see the exact logic.
Is that basically netcore?
Yeah. So this is a variant of netcore, and it's a variant of netcore compilation.
You say it's a variant. What does that mean? Is there really there's not really more than one.
Oh, well, I mean, if you read the Popple paper, the Popple paper has netcore, and that is not this netcore.
Okay, so you
There's
mean
no sequential composition in it, so it's
okay. So
yeah.
you're just being technical about it. I mean, basically, there is one netcore now that's sort of the accumulation of what we have learned minus clean stone. That's what you mean by
yeah, more or less. There are some subtle differences in terms of things like I think the last version of netcore at Cornell, before they threw it out and went to netcat, had a concept of flood, like the OpenFlow flood, which doesn't exist in pyretic. Never has, never will. Yeah, but I'm not sure. But so I don't know all the details, so I'm hedging basically. Okay, so now we're going to go through and look at our next one. So we got star drop. Well, that's going to produce nothing out, so this can't get matched. So we'll just get a little star drop. And this is our whole thing. So when we combine matching and forwarding sequentially, we get a classifier that says if f equals v forward out port 1, otherwise drop, which is sensible. So let's now go down, and we go down to our next leaf. Oh, look, it's the exact same one we've already compiled. So there are some different ways of caching things. You could imagine for recompilation, perhaps caching based on syntactic representation of policy. And I think that's what some of the SDX guys implemented. There are pros and cons to that approach. But for right now, we're just going to look at compilation itself and say, OK, well, we've got this one. How do we apply negation to it? Well, that is actually just a simple linear thing. And the way it works is any place where we had an ID, we turn it to a drop. And any place where we had a drop, we turn it into an ID. If we have anything else there, then we error out because it's not valid to negate something that isn't a match or some derivative of match. So you can't negate a modifier. So f equals v now is drop, and star is equal to ID. So this says if f equals v, we're going to drop. Otherwise, we're going to pass it through, which is exactly what we mean by not match f equals v. And now we're going to compile forward 2, and now we're going to do another sequential cross the exact same way as before. You'll see f equals v drop star forward 2. Okay, so we've got 2 sensible policies here, 2 sensible classifiers. And now we're going to combine them by doing another cross product, this time with a different nature, parallel composition. And so, as Jen had mentioned before, we're going to get to see how you can have multiple in parallel here. So f equals v, or actually we won't, because, well, we might. Anyway, f equals v. So first entry on this table, first entry on first table, first entry on second table, we get f equals v as our match. So they intersect. So this is definitely set intersection for parallel. Yeah. And the actual actions we get are forward 1 and drop. So this is parallel composition of forward 1 and drop, but we know that when you're parallel composing forward and drop, that's just forward. So I didn't bother to do that. Show all those steps in the slide. But so there's parallelizing here. Oh, okay, cool. F equals v and star also intersect on f equals v. And forward 1, forward 2 in parallel give us forwarding out port 1 and forwarding out port 2. Great. Now f equals v drop, again, f equals v is the intersection, and now the action is drop, or the open flow, not open flow, the pyretic policy is drop. And finally, star drop, star forward 2 gives us star forward 2, comma, drop. That's just forward 2, so we remove it. And that's our final classifier, except you'll note something. Of these 4 rules, only 2 of them can ever be matched. Because if a packet comes in that with f equals v, it has to match the topmost priority rule. Hence, leaving the other 2 f equals v rules in shadow. And I did not animate this. Basically, what happens in the runtime system is we do another pass called shadow detection, where we detect all of the shadow rules, or at least as many of them as we can efficiently detect, and we remove them from the classifier, thereby reducing classifier size. Because if you notice, because the nature of both parallel and sequential composition is the taking of a cross product in some form, what we have is a geometric growth of table size as we have height and true. Therefore, we need to cut down on this so we don't have such a huge table, we can't fit it in and spend so much time calculating over its entries in each pass as we do compilation. So we do shadow detection and removal in current pyretic compilation.
So you have,
and this is derived from, but far simpler than the shadow detection spoken about in the Popple paper.
so if you have a bunch of forward modules that somehow follow that class product, they're just boom, 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 boom. You can just ignore the latter ones. You can be inefficient at the higher level.
Yeah. So,
shadow detection.
Exactly. You can be efficient. You can be inefficient in your semantic representation via the pyretic DSL. However, when you do so, you may make compilation more expensive.
Trade-off.
Yeah, exactly. That's the trade-off, but it's it's not an unreasonable trade-off. So at this point.
So did you show these slides You showed it to somebody?
Yeah, I shared them on the Dropbox links that I sent. link that I sent out to the mailing list. Okay, so I think this is a good place to take a break after we do some questions. So are there questions that folks have for right the moment? Either folks who are at home or folks who are here.
Not related to this, but
Okay.
the email again.
Oh, you didn't get the email?
Somehow I got it.
This translate. Like,
Maybe you should have the mini-conf.
Yeah, I have that.
Yeah, so, okay, so I'll deal with that. Sorry, I blanked for a second. Does anyone at home have any questions for right now? Okay, so what I'm going to do right now is I'm going to turn off the broadcast. We're going to take a 10-15 minute break, and I'm going to email out another link with the new broadcast link. And I may have, since pretty much everyone here has a laptop, we might try something different. But we'll see. Okay. See you all in 10 minutes for whoever joins.